There is a question that sits quietly at the back of almost every human mind that has ever tilted its gaze upward toward the night sky. A question that arrives not with the sharp edges of formal mathematics, but with the soft weight of genuine wonder. How far away is that? How long would it take to get there? And buried inside that innocent wondering is one of the most profound misconceptions in all of popular science. A misconception so deeply woven into our intuitive machinery that even thoughtful, curious people carry it for their entire lives without ever stopping to pull it apart. The misconception is this, that a light year is a fixed, unyielding physical corridor, a rigid stretch of empty geometry that demands a fixed biological price in time from any creature bold enough to attempt crossing it. That assumption feels reasonable. It feels almost self-evident, and it is wrong in the most beautiful and mathematically precise way imaginable. To understand why it is wrong, we first need to feel the full crushing weight of what we are actually discussing when we say the words 1 light year. The number itself resists easy compression. A single light year is the distance that a photon moving at the absolute upper speed limit of physical reality covers in 1 full calendar year. That translates into a distance of roughly 5.9 trillion miles. Say that number slowly, 5.9 trillion miles. The entire diameter of our solar system, from the outer edge of the Oort cloud to the opposite outer edge, measures somewhere between 1 and 2 light years. This is not a short stroll across a familiar neighborhood. This is a number so large that the human nervous system simply does not have the ancestral wiring to represent it honestly. We read the digits, we pronounce the words, and the mind quietly replaces the real thing with a pale, scaled-down substitute. So let us try a different approach. Imagine a scorching desert, not a modest strip of sand, but a desert so massive, so brutally wide, that a healthy human being walking at a steady pace would require an entire lifetime every single day from birth to old age to cross from one edge to the other. You stand at the starting point, you look out, and you cannot see the far side. There is only heat and horizon and distance stretching away from you in every direction. Now your intuition, shaped by every physical experience you have ever had, tells you something very specific about that desert. It tells you the desert has a fixed size, that the physical ground beneath your feet is a permanent, stable, objective fact of geometry. The desert is what it is. The only variable available to you is how fast you choose to walk. Now imagine something different. Imagine stepping into a vehicle so advanced that it does not simply move across the surface of the desert floor. Instead, as this vehicle accelerates, the physical geometry of the desert floor itself begins to compress. The sand, the dunes, the scorching air, the very metric fabric of the ground mathematically folds ahead of you like an accordion being pressed by invisible hands. What took a human walker an entire biological lifetime now takes you mere minutes. And here is the critical point. This is not a shortcut. The vehicle has not tunneled through the ground or found a hidden path around the edges. The physical distance between the two walls of that desert has genuinely, measurably, objectively shortened. The geometry itself transformed in response to your velocity. That is not science fiction. That is the direct mathematical consequence of the most rigorously tested framework in the history of physics. Our current rockets, our fastest mechanical probes, our finest achievements in chemical propulsion represent an almost heartbreaking level of technological infancy when measured against cosmic scales. The fastest spacecraft humanity has ever launched, the Voyager probes, travel at roughly 38,000 miles per hour. That sounds impressive. Hold that number next to 5.9 trillion miles, and the arithmetic becomes quietly devastating. At that velocity, crossing a single light year would consume approximately 19,000 years of continuous travel, not decades, not centuries, nearly 20,000 years. The Great Pyramids of Egypt were constructed roughly 4,500 years ago. We would need to have launched that probe before the first agricultural settlements in Mesopotamia, before the invention of writing, before any of the foundational structures of human civilization existed, and it would still not have arrived. Through the rigid lens of Newtonian mechanics, through the physics of Isaac Newton, where space is a fixed empty stage and time flows at a single universal rate for every observer everywhere, we are simply quarantined, sealed behind a wall of stagnant distance that our biology and our current engineering cannot meaningfully breach. But the universe, it turns out, does not operate according to Newtonian mechanics at the speeds that genuinely matter. And this is precisely where the mathematics becomes not just useful, but genuinely transformative in the way it reshapes our understanding of what physical reality actually is. Albert Einstein published his special theory of relativity in 1905, and inside that framework was a set of consequences so radical that even Einstein himself had to sit with their implications carefully. The framework begins with two foundational postulates. First, the laws of physics are identical for every observer moving at a constant velocity, regardless of what that velocity is or in what direction it points. Second, the speed of light in a vacuum is the same for every observer everywhere, regardless of whether that observer is stationary, moving toward the light source, or moving away from it. These two statements sound almost modest. The consequences that follow from them are anything but. When you take those two postulates seriously and follow the mathematics wherever it leads, you arrive at a set of conclusions about the nature of space and time that fundamentally overturn the Newtonian picture. Space and time are not independent, separate quantities. They are two aspects of a single unified geometric structure called spacetime. And that structure is not rigid. It is not a fixed, passive backdrop against which physical events simply happen. It is a dynamic, flexible geometric fabric whose measurements genuinely depend on the relative state of motion between the observer and the thing being observed. One of the most precise and experimentally confirmed predictions that falls directly out of this framework is called length contraction. When an object moves through space at a velocity that represents a significant fraction of the speed of light, the physical distance along the direction of that motion, as measured by the moving observer inside that object, becomes mathematically shorter, not psychologically shorter, not merely appearing shorter through some optical trick of perspective, geometrically, measurably, physically shorter in a way that real clocks and real rulers aboard that vehicle would confirm without ambiguity. The contraction follows a precise mathematical formula involving what physicists call the Lorentz factor. As velocity increases toward the speed of light, the Lorentz factor grows larger, and the measured distance contracts by that same factor. At low speeds, the effect is so negligibly small that it is entirely invisible to any instrument we currently possess. But as velocity climbs toward the upper limit of physical reality, the effect becomes not just measurable, but overwhelming. Consider a spacecraft, genuinely advanced, capable of accelerating until it reaches 99.9% of the speed of light. At that velocity, the Lorentz factor is approximately 22.4. From the perspective of an observer standing still on Earth, watching this ship cross 1 light year of interstellar space, the journey takes slightly more than 1 year. The ship covers 5.9 trillion miles in just over 365 days. That is the straightforward result you would expect at near light speed. But now shift your perspective. Step inside the ship. Sit with the crew. Consult the clocks on the wall, which are measuring time according to the physical processes unfolding inside that vessel. Those clocks do not agree with the clocks on Earth. At 99.9% of light speed, with a Lorentz factor of 22.4, the crew experiences not 1 year, but approximately 16 days of elapsed time. 16 days to cross what an Earth observer measures as 1 full light year of distance. And if we push further, if we imagine a spacecraft achieving 99.999% of light speed, the Lorentz factor climbs toward approximately 700. The Earth observer still measures a journey duration of just over 1 year. The crew inside the ship experiences roughly 13 hours. 13 hours to cross 5.9 trillion miles of interstellar space. This is not a mathematical trick or a convenient approximation. This is the precise, experimentally verified behavior of physical spacetime. We have confirmed time dilation through measurements of subatomic particles called muons, which are generated in the upper atmosphere by cosmic ray collisions and should, based on their extremely short natural lifetimes measured at rest, decay long before reaching ground level. They do not decay before reaching the ground. They survive because from their own reference frame, moving at close to light speed, the thickness of the atmosphere they are falling through contracts to a tiny fraction of what a stationary observer would measure. They genuinely traverse less geometric distance. The muon experiment is not a thought experiment. It is a measurement performed and confirmed thousands of times by independent research teams around the world. Now let us return to that desert analogy with fresh eyes. The desert floor represents the geometric fabric of spacetime. The human walker represents our chemical rockets, creeping across a surface that feels permanent and immovable. But the accelerating spacecraft represents something categorically different. As velocity rises toward the ultimate speed limit, the physical geometry of the desert floor compresses along the direction of motion. The 5.9 trillion miles between departure point and destination do not vanish from the universe. They remain fully intact as measured by any observer sitting still relative to that space. But for the moving crew, the physical distance they must traverse has collapsed. The universe itself, operating strictly according to the laws of relativistic geometry, rewards kinetic velocity with a compressed version of reality. What this means at a deep philosophical level is that asking how long it takes to cross 1 light year is not a question with a single universal answer. It is a question that depends entirely on the frame of reference doing the measuring. For the stationary observer, crossing 1 light year at near light speed takes just over 1 year. That is a fixed, unambiguous statement from that reference frame. But for the traveler, the biological creature inside the moving ship, the answer depends on how aggressively they have forced the fabric of spacetime to compress around their vehicle. Push the velocity high enough, and the subjective experience of that crossing shrinks from millennia to years, from years to weeks, from weeks to hours. There is something worth sitting with here that goes beyond the mere mechanics of the numbers. The universe we inhabit is not constructed from rigid, fixed distances that impose a uniform biological tax on all creatures equally. The geometry of space itself responds to motion. It bends and compresses and stretches in precise, calculable ways that are governed by the same equations describing the motion of every particle, every photon, every massive object in the cosmos. A civilization with sufficiently advanced propulsion technology capable of sustaining near light speed acceleration would not experience the galaxy as an impenetrable fortress of distance. They would experience it as a compressible, traversable landscape. The stars we see tonight, most of them dozens or hundreds of light years away, could in principle be reached within a human lifetime by a traveler aboard a relativistic ship, while thousands of years accumulate on the clocks of everyone left behind. The conceptual trap that most of us carry without ever noticing we are carrying it is the quiet assumption that space is a fixed room and that time flows at a single universal rate for everyone inside it. Newton built a magnificent physics on exactly that assumption, and it served brilliantly for centuries. But the cosmos operates at velocities and scales where that assumption quietly breaks down. Where the distinction between what is measured by one observer and what is measured by another becomes not merely a matter of perspective, but a genuine physical difference in the geometric structure of the universe as experienced from different frames. The light year is not a wall. It is not a permanent, unyielding sentence handed down by an indifferent cosmos to all biological travelers equally. It is a measurement, a description of how much geometric distance exists between 2 points as evaluated from a particular reference frame. And the deeper you press into the mathematics of special relativity, the more clearly you see that geometric distance is not the rigid absolute quantity our intuitions insist it must be. It is flexible, it contracts, it responds to velocity in a way that has been measured, confirmed, and built into the foundations of our most precise scientific instruments. The universe does not demand a fixed price in time for crossing its vast distances. It demands a fixed price in velocity, and how much time that velocity costs you personally, biologically, mechanically, depends entirely on how close to the edge of physical reality you are willing to push your ship.